Hey folks, it's 5 after. Let's get going. So Steve let me know that he won't be able to join, but we don't have many people who regularly join, so it could be a quick meeting this week. Anything anybody tried that they want to talk about? Yuri or Gautam, any?
No, I didn't have a chance to work on that.
I'm here after a long time. I just wanted to see like the progress. Yeah.
Okay. So given that, let me just share where I am at. I think Yuri kind of knows from last week what I did, but I can catch you up really quick, Gautam, as well. So
as you were doing it, I have a question. So from what you've seen, what's a good like an average baseline model to start with? If you have the one of those that you use.
Yeah, I think if you go back to the very, I don't know, maybe 3 weeks back or so, and I posted many of the links on Slack. Couple of them are fast AI models. They are useful because I think one trick that I'm having difficulty in the sense that I just it's more work, so I'm just put it off to try other things which are low-hanging fruit. But fast AI makes mix-up very simple. So there are a couple of fast AI based fast AI fast audio and also fast AI Librosa. And I think if I recall the fast AI, one of the two I can is definitely something that you can use as a baseline. Then there's a bunch of PyTorch related things that I am using, which form a good baseline model as well that you can then improve as I've done. And then if you want, the only thing I haven't done, and there are again multiple baseline models easily available for TensorFlow as well. And in fact, the TensorFlow ones are the ones which are using or which have used the TPUs as well. And I have not used anything that I don't understand. So I've stayed away from the TensorFlow models primarily because being not as familiar with TensorFlow, I want to make sure I understand the model I'm using, and that's been my laziness to not spend the time to get on top of that hurdle. But any one of those 3 sets of models, because in each of them you have like 1 or 2 variants. And I think other than the TensorFlow, I have posted FastAI as well as PyTorch based reference models that you can quickly pick up, modify, and use and get up to about a 0.9 score. I think
which one of us TensorFlow based? I missed that. You said it's TPU, it's using TPU, but
yeah, I can post a link to a couple of those. I'm not sure whether I already did point to those in Slack. If I haven't, I'll go check, and if I haven't, I'll post after today.
Okay, cool, thanks.
But the PyTorch ones and the FastAI ones, I'm fairly confident I posted the link.
Okay, thanks.
So those are all very explainable things which we have discussed the basics of and how they work. And they, can you see my screen now that I'm sharing? Okay.
Yeah.
Okay. So, again, since, and I'll talk to this and probably post. So to answer partly Yuri, your question, and then kind of to quickly catch up Gautam as well, since there aren't too many others here. Let me start at the very bottom and move up, which will also give you the reference to what I'm saying I posted. So for example, one of the things I used was this FastAI and Torch audio, not FastAI. the audio library that you can use doesn't really matter because Torch Audio, Fast Audio, and Librosa are all variants and mostly can do similar things. So it's not very important which one of those you use. At least it doesn't make much of a difference because they all eventually just produce spectrograms that you can then, the challenge is in moving and analyzing the spectrogram, not producing them. So I think those three are largely, to my knowledge, interchangeable. But this very bottom of the notebook uses Torch Audio along with FastAI code and a very basic setup, which uses the entire 60 seconds of sound to create the label. So it's like it's treated in FastAI as a multi-class, multi-label classification problem. And with a few lines of code, you're up and running and can get up to 0.62 level of performance. I think the FastAI Fast Audio one is a problem that I didn't bother fixing. This is more with something in the spectrogram conversion that I was not giving the parameters right. But again, I don't think this is slightly different base capabilities because it was using Fast Audio. But again, as I said, I didn't bother because I had the other option. So that's why the score is low. It had nothing to do with the framework as much as the parameters I supplied to convert to spectrograms weren't appropriate. And then this Librosa basic is just a notebook that kind of illustrates, it's more like a notebook which was used to do EDA using the Librosa library. And that also you can see gives a reasonably good starting point of about 0.59. This is private public score. Then the frameworks that I am mostly stuck with are, and these two are just variants of each other, the RFCX baseline. So starting with this guy where I have the 0.75 or the 0.71, the thing to understand about these notebooks is they begin the process of using the time period when the species sound is heard and chopping for a certain period of time or a certain window of time around the point where around the time point where in training where the species sound is heard. So this one, for example, is a 10-second chop around the time when the species is heard, and you train that as a single label entity. And then because in the test, you have, again, the full 60-second sample, what you do is you take 10-second chunk of 6 chunks, and you do a prediction on each of the 10-second chunks, and then just concatenate them and take the max to figure out the totality of species in the test. So that's what, beginning with the all-in-one RFCX, I begin to do. The stratified K-fold basically does the training with a 5-fold. In this particular case, you just, the thing just uses a single fold, whereas here you do a 5-fold validation. And again, when you do the 5-fold, you predict using all 5 folds, and you average the predictions, or you combine the predictions for each of the 5 folds for each of the 6 chunks, because each chunk is 10 seconds and you have to predict over the entire test thing of 60 seconds. So that's what this stratified 5-fold thing does compared to the baseline. And then for all of these, the network that I was using, when I say all, not the FastAI ones are RES, NET, ResNet, NET based, whereas these two are based on ResNest, NEST. And again, toward the end of the competition, we'll spend some time, because that's at least I'm not familiar. So we'll probably, I posted the link to the paper, but we can look at the details of the ResNest and how it's different compared to ResNet. At the end of the competition, we can go through that paper. But then then I started using just this framework because it seemed to yield fairly good results, and modifying the various parameters that goes into it to try and improve my score. And when I used a specific optimizer called ADAS optimizer, then that bounced the score up quite a bit nicely. I did the SGD optimizer that dropped it from what the ADAS did. But then, as we have discussed in prior discussions, the slide before I go back to the ADAM, let me talk about this. Here, the learning rate in these SGD, ADAS, and the baseline stratifold was about, again, I'm talking from memory, but it is it's 2e to the -4, if I remember. So I thought, okay, let me try a much higher learning rate of like a 0.01 and stuff. And you saw that it caused a significant drop. So it seemed like, for this network and for these kind of optimizers, it seems actually for this network, I should say, because independent of optimizer, using a very high learning rate actually caused the score to drop. So I went back and then, switched the learning rate back to what it was for these two guys. And I used the ADAM optimizer to say, do I really have to use this, weird ADAS one? And sure enough, it gave me really good score. As you can see, this score with just the ADAM optimizer is better, or the best that I've gotten so far. So that gave me, again, I'm stuck, or I'm still continuing to use the ResNet optimizer, and then the other parameters for like how big is my FFT window and how much I hop and all that are in the notebook. The thing here in the ResNet, what is done is to modify the ResNet last layer, output layer, to just change it, or I should say add a single layer to take the output layer of this ResNet and switch it to the 24 classes that we would need in order to get the species prediction. So I thought, as I explained previously in one of the sessions as well, I thought, okay, why don't we make it a more complicated, fully connected module and see whether that yields us a better score. And actually it didn't. It kind of went down, not by much, but that didn't help, at least it hurt. So that wasn't a successful experiment. Also, I tried with, going back to the simple, take the output and just predict the 24 species by adding a layer, converting from the output of the ResNet to 24 classes. Let's train with 2x. These are all done with 20 epochs. I tried with 40 epochs. And as you saw, my result with ADAM was better than the 40 epochs one. So as Arto pointed out in one of the previous discussion, it's obvious that it's, a kind of overfitting and it doesn't help things. Then I ran into trouble with, in fact, this is a funny thing, which is also, I'll point to something I learned, which is kind of interesting in its own. Didn't have the time to investigate that angle, but I was using the ResNet NEST from the original developer of ResNet's website that he had posted, or GitHub link. It turns out he was hosting it on a link that apparently limits the number of accesses that are done, or some such thing. As a result of which, I immediately started having problems like 2 weeks back of access problems with where the ResNet models were stored. So I was like, bummer. Now, what do I do? But as Arto had pointed to some of the, and I'd also found a reference notebook that compared a bunch of networks and stuff for spectrogram related purposes, which seemed to suggest that DenseNets work really well as well. So I switched, as you can see, from ResNet to a DenseNet 161, and it gave me comparable scores right away while using ADAM. The only change between these is the DenseNet versus the ResNet change. One of the other things I found out when I was using these spectrograms and two relevant change or multiple relevant changes I made in the parameters or a hyperparameter search to better scores was while converting to spectrograms, I saw that the framework or that I'm using the code and stuff specified a top decibel when converting to the amplitude or power. And I said, okay, let me make a change to not restrict it. But what I hadn't realized and later realized when I read through the documentation is, so I removed the top decibel restriction. But it turns out that the default thing, even if you remove this, is what the specification said, top dB equal 80. So I thought, okay, if I don't restrict the top decibel to 80, what does the result? But what I found out by reading through the documentation is the fact that actually top dB equals 80 is the default. So if I remove it, I'm leaving it at top dB equal 80. So it shouldn't technically have any effect. So that's kind of a meaningless experiment that I found that it was meaningless after I had done it. The one change I made as I continued to, and my goal here was to try to see how much I can push this. And I can tell you by this week, I've reached the end of kind of my experiment. So I think I have to make some fundamental changes to the methodology in order to push the scores beyond where I am at. I'm still not, I'll show you, I was able to get very close to 0.9, but not exceed it. I'm below that. The 10-second window that I talked about, one of the things that if you look at is it points to, hey, maybe if you reduce the window and took 5-second sample instead of 10-second sample around the time point of this PC's sound, then that could help you get better. And that is the case because with everything else being the same and switching the window size from 10 to 5, the network being the same, I got to 0.887, which is pretty good. And the high score I got up to that point. One of the things I noticed was in converting the sound files to the spectrogram, he had used one of the variables you can provide to Librosa or to any of the other things is a thing called power. And that means you can either convert the spectrogram to be, the colors in the spectrogram, which are indicative of either the amplitude or the power. It's kind of confusing because it's this change between amplitude and power is set by a variable which is called power, but the power can be 1 or power can be 2. Actually, it can be a float between 1 and 2. And he was using a power setting of 2, which means he was using power values for the plot within the spectrogram. I switched it to amplitude, meaning I gave a power equal to 1 in the Librosa conversion, and you can see that my score jumped a little bit, but again to the 0.89 value as well. And then another variable, as I keep talking about, is the number of FFT samples, and that number was originally 2048. I made it 4096, therefore called it high FFT. So now I am at 5 seconds, 4096 FFT samples, the power setting equal to amplitude using the DenseNet 161 network. And that so far has been my best score, 0.89346 on the private and 0.89. So you can see that I'm very close to the 0.9. But there were a few other tricks up my sleeve that I wanted to try. Thinking where, let me see how far I can push this. All of these, the basic framework I'm using also allows for augmentation of the spectrogram, but it's an augmentation in the video space. So, and I talked about this again, you can go back and listen to one of the things of what kind of augmentations are being applied. But what you could do, I found out, is you could apply, and there is a whole library. I think I posted the link. If not, I will do so this week, of audio augmentation. That is, instead of waiting to convert the real audio wave to a spectrogram and then applying video augmentations, you can actually augment on the audio space itself, then convert to video, choose to apply the video augmentation as well or not, and then try it. and then do your classification and stuff. So I thought, okay, let me apply both. Let me apply audio augmentation followed by video augmentation and see whether it gives me. Now, remember, the highest thing I reached is this guy, 89346, 88738. So I tried both with the same network. It, actually is less than this somewhat. So again, that didn't help. It didn't hurt a whole lot, but it did hurt. The other, then this is now starting with, oh, sorry, I skipped one. Here on this one, I just did the audio augmentation and left out the video augmentation. And you saw that compared to this guy, the thing dropped by at least 0.02. So then I said, well, let me not do that. Let me do the audio and then follow it by the video, not just the audio. And that got me back somewhat. But it seems like what works best is just augmenting the basic audio, chopped at 5-second interval, converted to spectrogram, and then you apply augmentations in the video space, because that's what gave me this result. One of the things I wanted to try, knowing that it may not help me a whole lot because most of my runs are similar. There's just network and parameters changed on the spectrogram. But I wanted to ensemble the various outputs I have had up to this point, because by this time I had gotten about 10 or 12 different runs. So the remaining, when you see ensembling my runs, what you will see is I was just trying to combine, let's say, the best DenseNet with the best ResNet score, augmented, combining augmentations with no augmentations, or augmentation, all augmentations with none, various things that I tried to combine to see whether my scores improved. And obviously, one good thing about it is I now have a framework set up to be able to combine in various ways, min, max, average of my output files. But you can see that while some of these got close to this guy, I'm still not beating it by any significant margin. I think this guy is the one that even maybe improved, 893 versus, again, this is 89346 and 88738 on the public score. I think 89341, this is probably the one that gets closest. But again, the takeaway I had is, unless you have some fundamental variation in things that you're trying to ensemble, which we know, right? If you have highly correlated things, your ensembling is not really going to help. If you have uncorrelated outputs, then the ensembling of various things helps you actually get your score to be much better. But in this case, most of my results, I guess, are correlated. I'm just changing parameters on basically the network is the same. So other than ResNet and DenseNet, so you can see that that wasn't very successful experiment. Was not very successful. So those are the various ensembles. One of the things, and this was the thing I also tried last week, is, as Steve pointed out in Slack, to me, there's no reason to just use the ResNet from the original guy's website. There's also a TIM website that I can get a ResNet model from. So I set it up to take the ResNet model from the TIM website, kept all the other parameters the same. That gave me the best results for DenseNet 161. And lo and behold, you can see that my score didn't even match the previous results I had gotten with ResNet. That was somewhat surprising to me. So I used variants of the 50D that I found in TIM, and then I bumped up the ResNet to 101. And none of those ended up giving me even as good a result as I had seen with ResNet previously that I used the ResNet model directly from the developer's website. So what this tells, and both of them, obviously, I use pre-trained equal true. So I just use the model's weights pre-trained by, ImageNet. But what this tells me is that the models aren't exactly the same, at least the model and I went back, there was some problem with the original guys, and I went back and tried to download that and reuse it. But he claims the problem is fixed, but I still find that the problem of using his model continues to exist logistically, meaning it's not a problem with the model per se, but it's just where he's storing it, and there are access issues, and then he has moved it somewhere, and that has some other files missing, blah, blah, blah. So there's still problems of me trying to get back to the best score I had using ResNet models. But what is interesting is, even though the two models are supposed to be identical, they are not in practice. So that's something else to at least keep in mind while using models from websites and stuff is, there are subtle variations, even if the models are quote unquote claimed to be the same. That was an interesting finding. The one other thing which I discussed last week with Arto is, in all these up to this point, all the models that I'd used the resizing of the spectrogram that's provided by Librosa to a 224 by 400 size image. So I was using a 224 by 400 size image, even though the Librosa produced spectrogram for the 5-second window or the 10-second window could be a different sized image. So what I was interested in is in finding out whether the size of the image has, because obviously size of the image can have an impact on the, the resolution of the spectrogram. Therefore, does it have any impact on my performance? So I did it with no resizing. So whatever output size of the image I get from the spectrogram, I just use from the Librosa output of a spectrogram, I just use that. And you can see that that score is less than what I get when I resize to a 0.22 to image size of 224 by 400. So then I was curious and I tried 256. Actually, what I tried here was originally a 256 by 512 size. But what is interesting is, because I'm storing all the Librosa outputted spectrogram of my training in memory rather than writing it out to disk and then reading it back from disk and then processing it, the Kaggle run ran out of memory when I tried 256 by 512 for each of the 5-second chunks. And that's somewhat understandable, because if each of these chunks is that big, and then you have and actually during training it didn't hurt, but again, remember that during test, I'm again on top of these chunks, I'm having the chunking of 6 of that, because it's 60 seconds, so I have to combine 6 of these to get my inference. So somewhere along the way, it just completely ran out of memory and barfed all over me. So then I reduced it to 256 by 400, which is still a little higher resolution. And I was saying it's more the resolution in the frequency dimension than in the time dimension that I would be more interested in. So I did that, and that seemed to improve compared to this, but still didn't get me to the 224 by 400 performance level, if you will. So that says my 224 by 400 sized image, with all the other parameters being the same, are still the best results that I got. It's like we saw earlier, it was 0.893 and point something 87 something here, right? The one other trick that I wanted to try, or change I wanted to make before giving up on running out of ideas in this space, other than barring one idea of a mix-up, is to sample if you look at the output of some of all of these, there is some amount of frequency limiting going on after sampling at the basic sampling Librosa rate of 48,000. That's 48K. So the thing I wanted to try is, what if I don't sample as high? Because all you need, if your highest frequency in your sound, raw sound vectors is less than 16K, then sampling at 32K should be good enough for you, because half of 32K per the sound things, if you listen to the detail, the Nyquist theorem states that you are good enough. If your highest frequency sample in your samples is 16K, then 32K should be enough. Is less than 16K, then your 16K should be good enough, which is your base sampling rate should be twice of that. So 32K should be plenty enough. But one thing to keep in mind, when you do the resampling, because you provide it as a sampling input to the 32K, and it has to resample the raw data, because the raw data is sampled at 48,000. So that takes a heck of a long time to generate the spectrogram. So just a FYI that if you change the resampling rate from 48,000, which is the default, and it's also what they have provided, then beware, because it's going to take you a long time to generate. I mean, when I'm talking long time, it takes multiple hours overall to run the thing. Whereas, if I run it with the base 48,000K, 48,000, not 48,000K, 48,000 sampling rate, then I finish in less than an hour. This may take 2.5, 3 hours. So it's like a 2x to 2.5x multiplier. So I tried that, and that didn't, these two are identical, because I just made a mistake and resubmitted same thing. But bottom line, that's where I'm at, not at this level, but at, because these are all experiments which fail to improve the score. But the best score, therefore, that I've seen so far is the basic 161, this guy. 89346, 88738. So a 5-second window, 4096 FFT, power setting, amplitude, DenseNet 161, image size 224 by 400. So that's, it gets close to 0.9, but not above it. And the one thing I haven't tried, which I believe from everything I've seen tells me it should give me a boost and get me across at least the 0.9. I still have a heck of a long way to go to where the top guys are, which is 0.98. So that's still a long journey, but I wanted to see with this setup where I can get to. I believe I can get to 0.9, but I'll have to do mix up in order to get there, because the mix up definitely seems to improve scores quite a bit from everything I've seen. Sorry, Yuri, you were going to ask something.
Yeah, I think I misunderstood, and I apologize for sound. I think I misunderstood what 5-second chunk is. So they actually take where the useful sound is, and if it's like, let's say 13 seconds, they would split it into 3. Is that?
No. Let me explain the file. So see, in the test, in your test file, what is provided in your test data is for each record, you are given the Tmin and Tmax. My apologies for this background sound as well. There's some work going on in my house and can't avoid it. Apologies for that. But the Tmin and Tmax are provided around the point where the species makes a sound, and the species reference index or label is provided as well. So let's pick on species 5 as an example. So in the record, when if species 5 exists, then the Tmin, Tmax, Fmin, Fmax are provided. So what this notebook does is it uses the Tmin and it uses the midpoint of the Tmin and Tmax to locate the midpoint of where the species sound is from a time perspective, and takes a 5-second chunk centered at the same point where the center of the Tmin Tmax is. Okay, so you can think of it as 2.5 seconds before and 2.5 seconds after the midpoint of the Tmin, corresponding to the sound of the species 5. Okay, for a particular record, and it goes through each of the records and says, in this record, which species exists at which point, and takes a 5-second chunk around that point and makes a prediction on that and trains to predict that label.
Okay, so assumption is that in the middle, that's like the most, the loudest and the most specific, you know, sound of that bird. Or
no, I mean, you are anyways using the spectrogram of 5 seconds around, right? So you don't need to assume that in the middle is the best intercept. You're just saying the spectrogram of the 5 seconds around that, because Tmin and Tmax anyways are given. So let's say Tmin and Tmax are, I don't know, 15 seconds or 13 seconds around the total of 13 seconds, and it says from the middle of chunk of 5 seconds is a good enough sample to tell me the sound of that bird from a spectrogram perspective. I don't need all 13 seconds of that.
Okay, got it. Thank you.
And then obviously, you are now at a 5-second granularity in prediction, but you need to predict over the entire test set, which is, entire test set time duration, which is 60 seconds. Therefore, you have to apply the 5-second window and slide it, so to speak, through the 60 seconds. So you would actually get 12 such slices that you need to then combine to get the totality of the species in the test set. Does that make sense? So you can say in the 5-second, what is the argmax I'm getting? What is the max of the 24 species that I'm getting? I got one result. I do that for 12 chunks, and I'll get a result of from that particular values. And I have 5 such models because I'm also stratified k-folding. So I will get, as a result of that, 5 models. So I use the combination of the chunks and then the 5-fold thing to eventually produce this label ranked output of submissions.
Okay.
Right now,
thank you.
That's how I get to it. The difference that, and Arto was trying it, and I think he posted a link. I'm not sure whether he posted a link to his notebook, but in the FastAI notebooks, if you go to the bottom where I started, the difference there is they are doing multi-label, multi-class prediction on the entire 60-second training window. So they're saying, forget about, they're not using the Tmin, Tmax data that is provided or the Fmin, Fmax, and they're saying, I'm just going to predict what labels, get a spectrogram of the entire 60-second window of training. And once I got it, I also have the labels, regardless of time, of birds, which, or frogs or whatever, the species that occur in this 60-second spectrogram. And I'm going to try and learn that. And I'm going to predict it. Now, prediction is easier in that case because the training is on 60 seconds, multi-class, multi-label. I predict on a multi-class, multi-label of 60-second output as well. So there is none of this chunking and anything else going on. Right? But the results obviously are not that great. And in the process, I learned one thing, which is kind of, I'm in the process of kind of listening, and I deliberately didn't want to listen to the whole thing that you posted, Yuri, of the San Diego thing, because I didn't want to get to, okay, what are the best teams doing part, which I, want to struggle through a few more weeks to see how far I can push with other known methods before we get to that stage, if you will, of the competition. But one thing I learned by listening to that and by reading up a few more posts is it's interesting as to how they have gathered the data, which leads to a problem with the data that at least we should be aware of, that any of the methods that I've discussed so far might have a bearing on, how well or how poorly they do. So what do I mean by that? So apparently the guy, and I also, I think early on posted a reference to the paper that refers to how, the way they collected the data and such in order to generate the input to this problem. So in the training, apparently, or to get to the training data, what they did is they figured out, they gather all of this data of raw sound files from, microphones placed in forests and blah, 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 and so on and so forth across the world, right? And they collect a ton of raw data. Now, the question is, if they just were to employ human beings to listen to all that and mark all the places where potentially species could be, that would turn out to be tremendously expensive to them. So they said, that's not what we're going to do. What we're going to do is ask the expert to give us a template of where the a template of the best sound of a species. And then we are going to use that template and slide it over all of the input data that we have. And whenever there is a template match, we'll say that that's with a tmin, tmax, and an fmin, fmax specified, we'll say that's sound of that species. Okay, so that's how they generate the training data of 60 seconds, right? So that's how they have eventually ended up with the training data that they provide to us. Now, as far as the test data is concerned, what is interesting is the test data, they obviously wanted to be very precise. So in the test data 60 seconds, what they have done in every case is ask the experts to go in and actually confirm that if in the test, if a species exists, it's been confirmed by a human that that species at that time is precisely correct. Whereas in the training data, it's only the template match that's making the prediction of whether the sound produced by the species is in that tmin, tmax, fmin, fmax, and in that 60-second window. What that causes, apparently, and many people have eventually found it, and therefore we will need to find a workaround to solve this problem, is this fact. And the fact is that there are mistakes in the template or in the template matching. And because of that, there are missed labels in the training data, which means that there could be a template that actually should have matched, but it didn't. And therefore, there is a sound in the training file, but it's missed. Okay. So missed meaning it's there, but it's not labeled. So there are missed labels in the training data, apparently. And how we get around to, obviously, if you just trained with those missed labels, you're not going to get, a good result. But that's where I think, and I'm yet to confirm because I have to read through the mix-up and the labeling related paper to refresh my memory. At one point I understood, now I don't quite grasp the concept in detail. This is one of the reasons why I believe that mix-up could also provide potentially improvement in score, because it combines a couple of different things and softens the model's confidence level in its predictions. But I need to dive into mix-up and labeling related modification that can be done to improve the scores.
Hello, Srinivas.
Sorry?
Sorry, I missed the beginning of the session today, and I haven't done much with this competition this week, but that's really interesting what you find out about the training data. And I think that this pseudo-labeling and this meta pseudo-labels paper, which I mentioned during the previous unsupervised session, or maybe introductory unsupervised session, those are dealing with this problem of noisy labels. And yes, it's pretty interesting, and we probably can try out relabeling the training data, right?
Yes. So in fact, that is one of the methods. I went again, as I mentioned, I wanted to try to push this basic infrastructure I had as far as it goes. I've kind of seen where the limits of it are, plus minus the mix up approach, which I haven't applied. But exactly also to fortify your point, Arto, the thing that I also found out is the following, right? Or at least this is more a terminology that I wanted to kind of, that I learned in the process is, the method I referred to where fast AI is set up where you, and this kind of what you're doing, or at least the notebook I saw or approach you were trying earlier, right? Which is over the 60-second window, if I predict where what the multiple labels are, or even in my reference, the fast AI where I'm doing it over the 60-second window, apparently that is in an audio sense, apparently that is called weak labeling. It's called weak labeling because basically what it's doing is saying in this 60 seconds, you will somewhere in the time and with a matching of the frequency, find these 4 labels. What it doesn't do is tell you the exact time and the frequency bounds of the sounds in that window. Apparently, what is strong labeling is the thing that actually the test data does provide us, which is here is the example of a sound at this Tmin to Tmax range and in this Fmin to Fmax range within the 60-second window. Apparently, that's hard labeling. And there have been, I think, approaches. Again, I haven't looked at them in detail because, as I said, I don't want to get into too much of what are the best guys doing until, struggling myself to get there, to understand what they are doing and why it matters. But apparently, there are approaches that are applying this difference of weak and soft labeling and this additional concept I referred to either in the deep learning PyTorch or the unsupervised learning class of knowledge distillation, which is, train a model, or otherwise known as teacher-student training, where you train a model and then pass that information to another model to get that model to either perform better or to learn better, or to learn in a simpler model. That is a technique that I believe is also being applied in this context, because which is essentially a combination approach which combines weak learning with this, or weak, weak labeling with strong labeling.
So I have 2 questions. Kind of, first, I didn't get where. I don't think we have weak labels here correctly. But my actually question is about the training labeling problem. So if you don't use the fast AI approach that you mentioned in the beginning, if you use a 5 seconds interval, then the fact that you have missing labels, missing like actual sounds, it really doesn't matter that much, right? Because you're just not using that data. You're not using it incorrectly. Is that correct?
That is correct. Conditional to in the 5-second window, you're not missing anything else that's there, which you have reduced dramatically by going from 60 seconds down to 5 seconds. So that part I agree, but conditional to that, yes. And to your first comment, Yuri, I agree with this additional caveat. We do have strong labels in this competition, I agree, but you could use if you ignored, because the fast AI ignored the time points where the labels were provided and just said, over this 60-second window, I'm having all these labels, right? And try to learn that. it did not in any way, we did not provide hard labels to that approach, or that approach chose to ignore the fast labels and just used weak labels. And I wouldn't have understood this weak label, fast label terminology itself if I didn't understand what I just explained. So that's why it was interesting to me. And then I know that in some of these techniques, somehow they combine these in order to get a better model. Does that make sense?
Yeah, got it now. I think I missed the introduction. Why you look at weak label. Thanks.
Yeah, so that's really like interesting. Like we could start with this hard label approach, right? To train a model, like to react strongly on the samples where we like sure about the label, right? And then we can move to like, because as I showed, yeah, and I'm not 100% sure that those if you remember those GradCam outputs, if those are really like precise, but if I was interpreting that like correctly, probably that was like showing us that actually network like kind of we can say that it attends broadly to the all 60 seconds interval, while we like could expect it to attend somehow to this labeled intervals, at least in some cases. But I haven't observed it. On the other hand, like that, one submission that I made, as I said in the previous session, that I made a submission with like ResNet 18 and this straightforward approach with training on the whole spectrogram for 60 seconds. And the score wasn't really that bad, right? So probably it learns something, but maybe it will learn better if we start with like hard labels, as we call them, right? And then we go with that. Basically, we can say like intermediate training. We can use it like as intermediate training task, right? And then move to weak labels.
Yeah, I agree, because even what I went through, like from the bottom up, is you get 70% or a good 0.7x scores with training on the full 60 second, as I think my data shows. So with a ResNet and stuff, training on the whole thing, you can kind of get or fast AI ResNet 18 even, like you say, you can get to the 0.7x domain. And exactly to your point, it then is an interesting thought experiment on what combination of hard label and fast label and the approach or architecture to combine this data in creative ways that will get you to a much better score.
Yeah, another like, have anyone tried those pre-trained weights for like on spectrogram? I shared because I tried those and haven't observed any, like not any, but much improvement. So like there was like pre-trained weights for ResNet 18 as well. And like the start was different, like the beginning of training, but the final result wasn't better than like as compared to starting from ImageNet pre-trained weights for ResNet 18. So I don't know, maybe I'm using those wrong way. Maybe something is like in data processing is not matching what they used. Yeah,
Good question, Otto. I'll try to use one of those as kind of within my setup to see whether I get any better or different results, or is it the same? That's a good thing to try.
Yeah. Also, in one paper, which I was like checking for those pre-trained networks, I think they had like much worse results with ResNet 18 and started getting good results only with ResNet 34 or something like that. What they used. So
yeah, and given my setup uses ResNet 50D or DenseNet 161, I can quickly tell you whether those larger networks make a difference. But do they have pre-trained weights for that kind of networks, or is it basically just for ResNet?
In that latest repo, they had only ResNet 18, I think, from ResNet and some other like VGG-like net. I'm not sure, but yeah, there was only ResNet 18. And maybe that was really like fresh. So maybe they will upload more pre-trained models later, or maybe they are uploaded already. I will check that.
Okay.
And in another repo, I think they had like ResNet 34, but and maybe ResNet 50 or something like that. So yeah, but that one is kind of older, and yeah. So and I haven't like observed any better results with that as well.
Yeah, and as I keep pointing out, and it's I think time to try to explore those those new directions that I mentioned, barring again one simple things like using pre-trained weights or mix-up or label smoothing. But the other thing to highlight is we haven't at all yet done use the false positives. And in the context of what I mentioned earlier that I learned is the false positives are also very good data, because the false positives have been also judged by the humans. That is, they, when they did this template matches, in order to get the test data, where I said the test data is very precise, that the humans have actually judged the test data and said, no, this is absolutely, I'm sure that this is absolutely the right species at this right time. It is in the process of doing that, apparently, that they also found instances where the template or other things were saying, this is a match, and the humans listened to it and said, no, this is not a match, and this is not that species. So they took those and dumped it into the FP. So the FP is also very good data in that sense, because humans have checked that that sound which this template thing says is a frog X is actually not a frog X. So that's a high confident negative sample. So that's where this contrastive loss that we have talked about in deep learning, PyTorch, blah, blah, blah. If we can take that approach and use this Siamese kind of thing. Now, it's a pain to do. I've been thinking about it and my head hurts, because we, right now, at least, I'm storing all the data in memory as I go along. And now I have to identify, when I bring in the FP data, then it would mean that I have to identify pairs from the chunks which are identical, correct, and choose from the FP false positives to provide the contrastive examples. And if you can find that, then and provide this energy loss that Gautam just went through in the deep learning thing and used one of those, I don't know, NNMLI or one of those kind of contrastive loss examples, then there's an excellent test case to see how well a contrastive loss approach works, where you have a true positive and a false positive, and then train it and see how well it helps us in prediction.
That actually, if you like learn how to do that, I think that's very like powerful beyond this competition, because that's a typical setup in a lot of cases, right? Your model gives you results, and then your users review it and they say, no, it's not. So you have a lot of real world cases. I'm assuming that you'll have that labeled, a high quality labeled set of false positives.
Yeah. So that's how the false positive data they are provided comes about, apparently, and which says leaving that on the table is not good, that somehow we need to find a way to use that. And obviously the way that I can think of, given what we've learned from the deep learning Python course, is this contrastive approach.
Like another possibility I see to use these false positives is if we will do this relabeling of the training set, right? Like our labels on training set are noisy. And when we do relabeling, like in this teacher-student approach, we might use this false positives to clean up our like soft labels that we will, or like hard labels, whatever, that we will generate by teacher model, right?
Yeah, so that's true too. If you can find a way, you're saying, to compare and thereby eliminate, but from our own predictions, what are likely to not be true.
Yeah, and another
but in that case, Arto, how would you, meaning like you would predict, and then on what basis, because you're just predicting, on what basis would you or how would you go about comparing the FP samples to what you are predicting? Meaning,
yeah, that's like a hard question, because we don't have really, we don't predict this timestamps.
Yeah,
right?
exactly.
We just predict
the label.
Yeah, but we could also try relabeling it piece by piece, right? We could generate labels by in this sequential way, basically as you do in your notebooks, like current notebooks. You just like slice the audio, right? And like push it through the model, get the predictions, and then you do like argmax or like not argmax, but max pooling over the predictions, right? But we can also like clean up the predictions before that, right? So we have like we will have like an array of predictions associated with like with certain time intervals, and we can clean up that before max pooling, right?
Yeah, but so, sorry, go ahead.
Yeah, I just think that probably we would have to try to figure out if it would work.
Yeah, but definitely those are, I think, some of the interesting learning that's still ahead of us in this competition, I feel. So there's the push from getting where I'm at to get to where some of the best guys are will, in my opinion, and I don't know this for a fact, but I think will necessitate some of these thoughts to be applied.
Yeah. So I have like another questions. Is there like any data how good human performed on this competition, like on or rather on this task? Like what are human performance here? Because we are kind of relying on human labeling, but humans might not be perfect as well, right?
Yeah, I can see whether I can get a post or to the original paper that talked about. In fact, the I'll see whether I have downloaded that paper or I have a link to the paper, because one half of it I think discusses pretty much the first half of it pretty much discusses the method they use to generate the data. Yeah, and again, I'm not sure it's exactly this competition data, but they talk about generating species kind of data. And some of what I mentioned previously is from my listening to the link that Yuri had posted. I specifically avoided listening to the part where he gets into how the best teams or the top, he just used, I think, some number of examples maybe. But I kind of skipped over that parts because I didn't want to hear it before myself struggling with it. But barring that, the first part of his thing is about, what the data looks like, what's the binary sound approach, blah, 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 which we've gone through. But the interesting part was, and I had read it way back, but it had skipped my mind. So it jogged my memory about, him talking about how the data was generated and stuff. So if anything, Arto, the answer to your question might lie in that paper, but I haven't looked at it in a long time. But to your point, the data, but one thing I'd like to clarify is the data was not actually all human labeled. So as I explained, the steps were collect all the data, collect labeled strong templates from humans. And since they are just focusing on generating that particular example, I don't think the humans would be wrong, because it's like saying, and again, they might have taken an approach of getting 3 of the experts, 4 of the experts to all agree on a particular positive example, that this is a very good example. Then they made it into a template. And then they ran those kinds of, let's say they have now 24 templates, one for each of the species that they are wanting to find in all of the raw audio. Then they run this template over all of the raw audio data they have, and for a 60-second time samples, they label when the template matches and give it the corresponding template label and template time delta. So there, in generating the templates, which are the reference templates for the template matching exercise, and the template matching exercise is what generates the training data. So I think that I wanted to clarify, because it's, the humans wouldn't make a mistake in that process. And the test data, again, is they are just the test data they might have, but I'm assuming that there again, they wouldn't just rely on validating the 60-second test data from one expert, but would correlate it with multiple experts.
Okay, thanks. And another point, like I think usually when doing this contrastive learning, it works best when you have like large batch sizes and lots of data, and so I wonder if we would be able to apply it to our problem, because we don't have that much data, right?
Yeah, that's a good point. Yeah, we do not have. Of course, we can generate true positives by what I think Yuri had mentioned in the previous deep learning lecture is, you can just augment the data and say, well, this is just an augmented sample of the same, so treat that as the same. The issue is in generating, well, I guess you could do the same with the false positives too. You could augment them and then throw them in as negative samples. And then you could augment the positive data and throw them in as positive samples, thereby increasing your data size. But other than that, I'm out of ideas of how to increase the data size. You're right. So Gautam, you've caught up on what, got a snapshot of where we, at least I'm at, and Steve couldn't join today, but he's made his submission, and I think Arto has tried a couple of different approaches, which are interesting too. So
Yep, that's a great summary. Thanks. I just wanted to like understand, was the label as well generated by the template that you mentioned, or is it just the start and end?
The label would be generated by the fact that the template is for a particular label, right? Because you would have, again, that's my understanding of what the guy explained. I could be wrong. I'll post a link to the paper and then I'll go through it myself. It's been a while. I just listened to the video of what his explanation was, but my understanding would be that you would use a template per species and run it through the entire audio sound. So once, if the template hits a match, it's for that label, right?
Okay, then why do they need an ML model if the label itself was generated not by humans? Then you just get the template and do it for the test.
But even running the template through all the audio rather than just using a model and doing the prediction is probably much faster, right?
Yeah.
Much quicker than having to run the template over all of the time that the raw audio exists. Here, you just have the model and have it predict. Still, I would imagine that it would be orders of magnitude faster. Because they're trying to automate the whole process, right? Of figuring out the species from the raw audio they are gathering.
So you're saying the model is faster than running a template?
I would imagine that, you just have a model and you say predict the thing over this, rather than running. Remember, you have to run 24 templates through all of that.
Okay. No, but if you have something that is equal to like gold standard of label, the best label, then why do you even need an ML model? That's what was confusing.
Yeah, I mean, if it weren't for prediction or the model giving you a much faster performance, as they continue to gather data, I wouldn't think that they would go through the exercise, right?
Okay.
But again, reading the paper might provide better answers to your question too, Gautam.
Which paper is that?
I'll try and post a link. The paper that I saw, which discusses, I think, the approach they use, and I'm not sure whether what I told you is what the guy in the San Diego machine learning group summarized. I know there is a paper, and I myself read it at the beginning of the competition and then set it aside, which refers to this approach. But I don't know whether what the guy described is exactly what is described in the paper. But I'll post the paper that I'm thinking of anyways, and I'll myself go back and check it to see whether his explanation of that is consistent with reading the paper. Because the paper for the first half covers exactly the methodology they use to generate the data. Okay, anyone else? Any other thoughts? So I think next week is going to be a little bit more of a challenge to try and apply some of these ideas and see where we can get to. Okay, if nothing else, thanks for joining everyone, and good luck with trying different things over the next week, and we'll convene a week from today. Thanks, everybody.
Thank you.
Thank you.
Thank you.
Bye.
Bye.